Hi, my name is Gabriel Moreira and I'll be presenting our paper Fast Postgraph Optimization via Krylov-Schur and Cholesky Factorization. Our paper addresses a problem that is common in robotics and computer vision, and that is the fusion of visual data on a common reference frame. Suppose we have a stream of images or point clouds, and our goal is to best align this visual information on a common reference frame so as to be able to estimate the trajectory and reconstruct the 3D scene. And we want to do it both optimally and efficiently. A popular way of solving this problem in the literature is via postgraph optimization, or PGO. So how does it work? Suppose that we have, for instance, a set of point clouds and we also have relative rigid transformation measurements between pairs of them, here denoted by m tilde ij. If we interpret this information as a graph, we can come up with an objective function that is maximized by the set of absolute rigid transformations that best align these point clouds on a common reference frame. This is the gist of PGO. It is a non-convex and high-dimensional optimization task that is usually tackled via nonlinear iterative solvers. What we propose is called MAX, or motion averaging via Krylov-Schur. It's a very simple algorithm that comprises two steps, the first being spectral decomposition, followed by Cholesky factorization. We show that under a high signal-to-noise ratio, the solution we produce is optimal of a specific objective function and also takes into account the sparsity that is common to PGO problems. So how does MAX work? Well, like I said, PGO attempts to maximize a certain objective function. In our case, we derive this log likelihood function assuming a specific generative noise model. Now, unlike common PGO solvers, instead of attempting to maximize this function as a whole, we will split the optimization task in two. And this is possible, as we demonstrate in the paper, if there is a high signal-to-noise ratio. In this case, we can first tackle the rotations in what is known in the literature as the problem of rotation averaging to obtain a set of rotation estimates R hat. Once this is done, solving for translations is a least squares problem to obtain the set of translation estimates T hat. So we take PGO and we come up with two sub-problems. To tackle each one of them, we start with the rotations. We take the relative rotation measurements and we build a symmetric block matrix, here denoted by R tilde. Then we perform two routines in parallel. We normalize R tilde by the graph Laplacian and we perform a symbolic Cholesky decomposition. Then the output of these routines is used to call a Krylov-Schur eigensolver to compute the three eigenvectors corresponding to the three smallest eigenvalues. By projecting each 3x3 block to the spatial orthogonal group, we can come up with a set of rotation estimates. This is actually the set of ground truth rotations if there is no noise, hence the reasoning behind this algorithm. Then, to solve for translations, like I said, this is a simple least squares problem, and the optimal translations correspond to the solution of this symmetric linear system, which can be solved via Cholesky. Now, the caveat that allows for a considerable performance gain is the fact that we have already performed a symbolic Cholesky decomposition, so solving for translations can be done very, very efficiently. So this is the gist of MAX, these two steps. Now, how does it fare in practice? Here, I show you the maximum attained for 6 different PGO datasets, and we compare our maximum with that of the chordal relaxation method and Gauss-Newton implemented in G2O. You can see that for most datasets, the solutions are pretty much equivalent, with the exception of Sphere, where both our method and the chordal relaxation yield suboptimal solutions. Now, in terms of CPU time, this is where MAX distinguishes itself, and you can see that here in light blue, our solution takes a fraction of the time of other methods. Specific here, the GRI3D, Gauss-Newton takes almost 500 seconds, whereas we can solve the problem in less than a second. Here you can see the trajectories produced by MAX. You can see that they're fairly regular. So, bottom line, PGO is a difficult problem and we propose to solve it by a very, very simple algorithm that comprises a Krylov-Schur method for spectral decomposition and Cholesky factorization. We show that our solution is optimal under a high signal-to-noise ratio and can be computed much faster than alternative methods. The code is available online as well as several videos of reconstructions. Thank you.